The next topic is, now that we've started looking at actually using power in sinusoids, we saw that we calculated the average power, and for a sinusoid it was pretty easy. You're taking, we found using that multiplication, using that trig identity for two perfect sinusoids, you get that constant term out front. But we don't always in AC, we've dealt with things that have only sinusoids right now. But really, this could be any periodic function. And in fact, in modern power, a lot of times we don't have pure sinusoids. So like the power supply for your computer, power supply built into your television, lots of electronics nowadays use something called a switched power supply. So rather than using just a transformer, which we'll talk about in a couple of chapters, how those work, but rather than just using a pure sinusoid and trying to make that sinusoid bigger or smaller, they actually use a switch to very, very quickly turn the power on and off. And it averages out the power then that is received by our device. Switched power supplies don't look like sinusoids. They have lots of spikes. They get kind of crazy. And yet we still need to be able to calculate the power that they're delivering, because that's real. There really is power coming out of those things. Even with sinusoids though, right? We said if we just take the average value, you get 0, right? But for any kind of weird thing, right? So whether I have a sinusoid that looks like this, that's going to average to 0, or whether I have some spiky looking thing like this, right? How can I characterize these and talk about them all kind of in the same way? Like, how big is this signal? I'm not sure, really, because sometimes it's really big, but then it's really small for a long time. How big is the sinusoid? Well, I can tell you the amplitude, right? But, like, in general, it's varying all the time, right? So I can't really say. So when we're talking about the power being dissipated, that average power is kind of the thing we want to keep our eye on, right? We know there's really power being dissipated most of the time. So, because everything has resistance in it, right? So we develop an effective or RMS value to characterize any time-varying current or voltage. What this allows us to do is to avoid talking about this sine wave and saying, well, the average value is 0. Because even though, yeah, it oscillates to plus to minus, it doesn't give us 0 power. We get real power out of it. So we find its effective magnitude essentially saying what number could we attach to this that would give us, if it were DC, would give us the same amount of power as this thing actually delivers. Right? Because every time this is going up or down, anytime it's not actually sitting at 0, our resistors are burning up power. Right? That's energy going off as heat into the environment, right? So what value of a battery could I plug in that would dissipate that same amount of power? So that's kind of what we're trying to look for, right? So we can find that total power that's being dissipated, right, by saying, well, yeah, I know that I have an average value for my current, but that's not going to get me all the way there. If I look at VI, the voltage and the current are typically out of phase with each other, and so you don't end up with a 0, right? But if I look at any of the other ways of writing down power that we used to use before, right? We often said, power is not just VI, but it's I squared R. That's another really useful way of writing down power, right? If I know the current, I don't have to go through the hassle of finding the voltage. I can just plug in my resistance and find power directly. But again, now if I try to take an average of the current, it's 0. But if I squared that, right? If I square the current, then take its average, I can avoid the problem. Because anytime the current goes negative, its square is positive. Right? Now, if I take the average of that, right, by taking an integral and dividing by the period, I get some value up here, not 0. Right? So we take the average or the mean of the square. That's the M and the S in RMS. Mean and square. Right? And then if we want to know the true, what that value is, of course I've squared this. So I don't want to know I squared, I want to know I. So the I effective, right, is not the average of I squared, but the square root of that. And so that's the R. So RMS is root mean squared value. And this is giving me this value right here. That, again, is the value of current that would deliver the same amount of power to a resistor. Right? And so I can use the IRMS value to calculate power when I'm talking about sinusoids or phasors. Right? So now I can say instead of little I squared R, I can now use big I RMS squared times R. Because by doing the RMS, I eliminate that problem of having an average value of 0 on my current. So RMS is actually a much more valuable number to use when you're measuring currents and voltages that are time varying. And so a lot of your handheld multimeters, they will have an RMS capability. They do this for you internally when you're measuring AC. But you actually need to be very careful when you're looking at a handheld multimeter or any piece of lab equipment. You want to look for one that says, ideally, it will say true RMS. Right? Because there are even some that will look at it and do the calculation for you as though they are assuming it's a sine wave coming in. Those are not quite as accurate because, again, if it's not a pure sine wave, right, if I have one of these spiky things coming in instead, I can't really calculate it. But a true RMS meter actually does the integral over time, numerically, and gives you the output value, rather than assuming, measuring like the period and then assuming it's a sine wave, which would mess it up, because the true RMS of this is going to be something like this. Whereas if you had a sine wave of the same period, it would be something like this.
What, 707?
Yeah. Yeah, root 2 over 2. Right? So, true RMS is the best thing to look for on an actual meter, right? So, but that RMS value, right, it is a constant value, but again, it does depend on the shape of the function. We're only going to really calculate things most of the time assuming they're sinusoids. But there are some problems in the end of this chapter where they'll give you, a triangle wave and say calculate the RMS. Right? So you'll get a little practice doing those integrals. Remember, you're just plugging it into this formula. So whatever value of I you have as a function of time, plug it in. Take the integral. Let MATLAB take the integral for you. Right? MATLAB will do integrals really, really well, and it doesn't mind. And just remember here, what are we integrating over though? We're integrating over one period. So this is a definite integral where we start at 0 or whatever time we're beginning our period at, right? So 0 is fine, and then we stop at whatever the period of the function is. So if it's a second, you integrate from 0 to 1, and then you divide by 1 second, right? If it's a 2-second period, integrate from 0 to 2, divide by 2. So whatever this top value is, you're plugging that in on the bottom as well. Okay? So for the sinusoid, which we do see a lot, of course, because that's what comes out of our wall socket, right? If we were looking at the current flowing into this resistor, calculating the RMS value of the sinusoid, right, when we know in phasor form it's just the magnitude times cos omega t, we can, when we plug that in, you find, in fact, that the RMS value is just dividing by the square root of 2. Okay. So 1 over the square root of 2 is the 707, right? The 0.707. That is the right number, right?
636 for average.
Double check. Yeah, because yeah, square root of 2 is 1.44, right? 1 divided by yeah, 0.707. Okay. So anytime now that you see a sinusoid, you can immediately turn it into RMS by putting the square root of 2 on the bottom. Right? The one thing that makes that really handy is that when we're using RMS values of voltage and current, if we look at our expression we had before for power, right, for the instantaneous or the average power in, when we're looking at cosines and sines, we had 1/2 VMIM. Well, now the voltage does the same thing, by the way. It's not just current, right? Voltage is also a sinusoid. Its RMS value is the magnitude divided by the square root of 2. So I have a square root of 2 on the bottom of the voltage, and I have a square root of 2 on the bottom of the I. That's my 1/2. So when I'm using RMS, I don't have to remember this 1/2 out front, which is really handy, because now the effective power, average power, not I effective, but the power is just VRMS times IRMS times the cosine of the angle between them. Right? So that's a little bit easier to remember. Right? The other thing is that once you express your phasors in RMS, you should remember everything should be in RMS. If you do that, you won't run into trouble. But like if I have voltage in RMS and I not in RMS, I've got to try to remember one of these has the square root of 2 on the bottom, the other doesn't, and then what does my output come out as? Which one is it? Right? So if you're doing RMS, it's kind of like if you're doing phasors, everything's phasors. There should be no time domain stuff left, right? It's almost like that. If you're doing RMS, everything should be RMS, so that you have no problems. And in fact, you should get into the habit of most of the time just using RMS, right? Because it's going to avoid problems. It also puts you in the mindset of calculating your values, even if these weren't sine waves, right? If they weren't sinusoids, as long as you're doing RMS, it doesn't matter, right? It's fine. You get the correct values, right?